What is the size of our solar system? When we look at the sky on a clear night, away from the pollution of cities, we immediately realize that the universe is vast. It's only a feeling, perhaps based on naive and instinctive reasoning. If we see a lot of stars, say thousands, maybe millions of stars, this suggests the universe is really, really large. I mean, the planets themselves are enormous. We know that the Earth is large, but it is a small planet when compared to gaseous balls like Jupiter or Saturn. Regardless, it is significant for us, humans. We are so insignificant. Then there are the distances between planets or the distances between stars, which are difficult to visualize. It's difficult to gauge how far away the planets or stars truly are. Have you ever considered the size of our solar system? This question may appear to be straightforward to answer, but is it? Let us start with the facts. Light from the Sun would take around 555 days to reach the end of the solar system, compared to 8.25 minutes to reach the Earth. It's evident that we're talking about some immense distances that can be difficult to comprehend. In general, the diameter of the entire solar system is 100.000 times the distance between the Sun and Earth. If you could design and build a spacecraft that could travel at the speed of light, it would take about a year and a half to reach the end of the solar system. Don't worry, because it would be a very enjoyable trip. You would not be bored at all. Approaching Jupiter, for example, you'd notice that it would take 11 Earths to fit across its circumference. However, because we will almost certainly never be able to move at the speed of light, the journey may get tedious. Traveling at regular speed on a planet would take us almost 570 years to reach the dark, chilly, and blue Neptune. Of course, our perseverance would be rewarded by this breathtaking view. So yet, just one spacecraft has had the distinction of visiting this magnificent planet, Voyager 2. As a result, the majority of images we see of these two ice worlds come from this mission. It looked exactly like its sister spacecraft, Voyager 1. The probe is currently leaving the solar system and headed into interstellar space. Voyager 2 was launched on August 20, 1977, and NASA stated in 2018 that it has somehow reached the heliopause, the theoretical boundary where the Sun's solar wind is stopped by the interstellar medium. Voyager 1 was Voyager 2's twin, and it is the most remote man-made object. This incredible spacecraft has been in orbit for more than 40 years and has yet to escape the influence of our Sun. Voyager 1 is approximately 13.8 billion miles, or 22.2 billion kilometers from the Sun as of February 1, 2020, nearly 4 times the usual distance from the Sun to cold Pluto. That merely goes to highlight how massive our solar system is. In astronomy, the problem of distances was enormous. Astronomers had been looking for a basic unit of measurement for many years. The first one they devised was the Astronomical Unit, which is defined as the distance between the Earth and the Sun. However, measuring this distance is no easy task. It required a lot of research, work, and sharp minds to arrive at a reasonable estimate of this distance. The ancient Greeks estimated the distance to the Sun in terms of Earth radii using naked eye observations. Observations of parallax, the apparent shift in location of an object against the backdrop when viewed from 2 different positions, permitted increasingly accurate measurements of planetary distances from the 17th through the 19th centuries. Using radar and computing orbits from many photos, highly exact distances have recently been acquired. We currently know that this distance is 149 million kilometers or 92.58 million miles. It is practically a magical number, and if you are an astronomer or merely interested in astronomy, you must memorize it. The astronomical unit serves as the foundation for all distance measures in the solar system and beyond. Once you know the distance from the Earth to the Sun, you can make several observations of planets and use Kepler's third law to rebuild their distances. This provided astronomers with their first idea of the size of our solar system. All they needed was an instrument, a telescope, and a lovely law, Kepler's third law. It appears to be a simple activity now, but it requires a great deal of thought and logic. We now know that the distance between Earth and the furthest planet, Neptune, is about 27 billion miles. You might wish to compare this to the distance traveled by the International Space Station in 24 hours, which is 397,677,563 miles. Someone once remarked that if you can't describe something clearly, you don't understand it well enough. So, let's try to gain a better sense of the distances involved. Assume we wanted to represent the solar system to scale using some standard walkable units. These are the astronomical distances between the planets. Mercury, 0.4 AU, Venus, 0.7 AU, Earth, 1 AU, Mars, 1.5 AU, Jupiter, 5.2 AU, Saturn, 9.6 AU, Neptune, 30 AU, and Uranus is 19.2 AU. And no, we'll need to translate the astronomical units to something walkable before we can have you walk the solar system. We can complete this work by multiplying the number of astronomical units by 100 and measuring in cm. We may start with the Sun at 0 centimeters, then draw Mercury at 40 centimeters, and Venus at 70 centimeters. The Earth would be 1 meter from the Sun, and you would have to walk 30 meters to reach Neptune. In this instant, Usain Bolt could complete the solar system in just 3 seconds. But what if we wish to see things through the eyes of light? How long would a beam of exceptionally pleasant and cute photons take to travel the distances between the planets? Photons emitted by the Sun reach Mercury in 3 minutes, Venus in 6 minutes, and the Earth in 8 minutes. They're rather fast, aren't they? However, as we move away from the Sun, the distances between planets grow longer. It would take 13 minutes to get to Mars and 23 minutes to get to Ceres. Then you'll need to practically double this time to get to Jupiter, 43 minutes. Our photons will eventually pass Neptune's orbit in 4 hours and 10 minutes. However, Neptune is not the end of the solar system. They would reach the Kuiper belt after 5.5 hours, and around 12 hours into their journey, they would begin to depart the heliosphere and enter interstellar space. Crossing beyond the Oort cloud, on the other hand, may take them up to a year and a half. Given current technologies, I believe it is evident that humans will never be able to reach the end of the solar system in a single generation. Some scientists believe that you could travel halfway to Proxima Centauri before leaving the Sun's sphere of influence. That is, you would have to go to the next star in order to exit our solar system. Proxima Centauri is the nearest star to us, and our photon family would arrive after 4.24 years because it is 4.24 light-years away. This suggests that the Sun's impact stretches at least 2.12 light-years, or roughly 13 trillion miles, from Earth. That is simply enormous. It's best not to think about it, or you'll feel very small. Using current technology, crossing our solar system would take us an astounding 30,000 years merely to leave the influence of our Sun. That is a very long period for a human being, and it is also a pretty dull travel. In any case, we have some time to enhance our technology, and there's no need for us to leave the solar system. However, we are attempting to reach Mars. We will most likely see the first black person and woman safely landing on the Moon, as well as the first man walking on Mars, within the next decade or two. It would be an incredible spectacle for us on Earth, as well as a significant step forward for humanity. Mars is the 4th planet from the Sun, and reaching it with present technologies takes 7 to 9 months if you begin the journey in the most advantageous initial configuration. This is something that can be done, and we can't wait to see more. But what if we use the Parker Solar Probe, the fastest spacecraft ever built, to reach Mars? During its 10th close flyby of our star, the Parker Solar Probe attained a peak speed of 101 miles or 163 kilometers per second, which amounts to 364,621 miles per hour. According to NASA, when the Parker Solar Probe gets within 4 million miles, or 6.2 million kilometers of the solar surface in December 2024, its speed will exceed 430,000 miles per hour. If the Parker Solar Probe could achieve the speeds it did during its 10th close flyby of the Sun, and deviated from its Sun-focused mission to travel in a straight line from Earth to Mars, the time it would take would be, the shortest possible approach time is 93 hours. The closest recorded approach was 95 hours. The The longest approach time was 686 hours or 28.5 days. 384 hours, 16 days. On average, of course, the previous calculations have a flaw in that they calculate the distance between the two planets as a straight line, but engineers know that paths and orbits in the cosmos are constantly curved because gravity bends space-time. Furthermore, these calculations assume that the planets do not shift with regard to each other along the journey. But this is not the case. In actuality, the planets are constantly moving around the Sun in their orbits. That is why engineers must be capable of calculating the optimal orbits for launching a spaceship from Earth to another planet. So, in general, how long it takes to reach Mars, or any other planet, depends on where the two planets are in their orbits when a mission is launched. It is also dependent on technological advancements in propulsion systems. Photon propulsion, for example, is a promising propulsion technique. Lasers are fired at a reflecting material, such as a solar sail, to propel it. Though the photons in the laser do not have mass, they do have energy and momentum, and when they bounce off, they impart a little amount of kinetic energy to the reflective surface. With the frictionless vacuum of space, continual acceleration may theoretically propel a spacecraft to roughly 30% of the speed of light, similar to the speeds achieved with partial accelerators. It will most certainly be decades before photonic propulsion is employed for space travel, but the fact that the technology appears to work is reason enough to pay attention to it.